Okay, hello everyone. Thanks for tuning in today. So it's my great pleasure to announce today's speaker, Arkadiy. He's a PhD student and working on evolutionary algorithms. And today he's presenting his work it was a paper I think this year from ICML about multi-objective population-based training. And with that, please take it from here.
Thank you for having me here today. Indeed, the topic for today is multi-objective population-based training, and this paper was accepted for ICML this year. Today we'll talk about hyperparameter optimization, and first of all, what do we call a good algorithm for hyperparameter optimization? Well, of course, we'd like to have strong performance and moreover within a limited computational budget. Then we also don't want to have any huge additional computational overhead. And also we'd like our algorithm to be parallel and scalable, because if we have more resources available, we'd like to efficiently utilize them. And one of such algorithms is called population-based training, PBT. It works like this. So we have a population of networks together, hyperparameters and weights. We train networks with some usual training algorithm like SGD for some epochs. Then we apply ranking function. So we select the best networks and the worst ones. And then we apply so-called exploit and explore functions. So we copy good weights and replace bad weights. And we also copy good hyperparameters, replace bad hyperparameters, and apply some perturbations of them in order to enable exploration. And then we continue training our networks for some more epochs. So why is it good? So first of all, it's parallel and scalable. So ideally, without bottlenecks, the full search takes just one model training, simply because we can train the whole population in parallel. And also the computational overhead is super small, because this ranking, exploit, and explore operations are computationally cheap. And it was shown that it can be successfully applied in different domains. And one of the main applications was shown to be augmentation search in image classification tasks. But today we talk about multi-objective hyperparameter optimization. So why are we interested in it? So for example, we have multi-objective problems such as precision versus recall, accuracy versus fairness, and accuracy versus adversarial robustness. So in these cases, instead of searching for one optimal solution, we'd like to have a trade-off front of solutions, so trade-off between two objectives. Let's say that we'd like to optimize two objectives, and formally for more than two objectives, the multi-objective problem is formulated like this formula. And simply the main idea is that instead of just one best solution, we'd like to have a trade-off of them. And what algorithms do exist for MO-HPO? So the first algorithm I'd like to mention is multi-objective asynchronous successive halving, MO-ASHA. So basically it's random search with early stopping. So more resources are allocated to more promising solutions, which makes it more efficient than simple random search. And for multi-objective case, solutions are ranked using some specific ranking technique. I'll explain it in more details later. And we can also modify it further by adding a Bayesian sampler. And this modification is called MO-ASHA. And this idea is to make random search a bit smarter and to sample new solutions using this learned Bayesian sample instead of just randomly. We also have other Bayesian optimization algorithms for MO-HPO. They are not fully parallel, however, but I mentioned them because they are also strong baselines. And the most advanced algorithm of this kind is called parallel noisy expected hypervolume improvement. And what we can also do is we can use single objective PBT plus some scalarization technique, which can simply turn a multi-objective problem into a single objective one. So, for instance, we can use a linear combination of different objectives, or we can use these weights of objectives can be, for example, random, or we can take the maximum of this objective. And the whole idea of scalarization is turning a multi-objective problem into a single objective one. But I have to note that it's not a truly multi-objective approach because it just it's turning a problem into a single objective one. And we propose to extend PBT to multi-objective optimization in a truly multi-objective way. So we propose to use so-called domination-based ranking of solutions, the idea which was originally proposed in the non-dominated sorting function of NSJ2 algorithm. And the idea is the following. So let's say we have two objectives. We have multiple solutions. So each circle here represents a solution, and we'd like to rank them. So we say that solution A dominates solution B if in all objectives its values are better and not all of them are equal. And then we divide this set of solutions into so-called fronts. So inside each front, solutions don't dominate each other, and each solution in the first front dominates solution in the second front. All solutions in the second front dominate solutions in the third front, and so on. And this gives us a ranking. So we say that solutions from the first front, so green solutions here, are the best ones. Then go the orange solutions, and then go the red ones. And now we can apply this domination-based ranking technique to PBT. And this makes PBT a truly multi-objective algorithm. So in general, it works exactly like single objective PBT, but we use a generally multi-objective ranking procedure. And what experiments we perform? So we have different data set domains. We have tabular data. We have standard CIFAR 10-100 image classification data sets. And we have cellular data sets. So image face image data set. And what hyperparameters do we search in each task? So in precision recall task, we search, for example, for class weights in the cross-entropy loss, which is a natural way to balance precision and recall. In accuracy fairness, we search for the weight of the fairness regularizer function. So this way, we naturally balance accuracy versus fairness. And in the accuracy versus robustness setup, we search for the image augmentation policy, for example. And how do we define performance of a multi-objective optimization algorithm? We use two metrics. The first one is called hypervolume. So let's say we have multiple solutions depicted with the green circles here. We need to select the reference point, the green circle here, and hypervolume value is this green area here. So basically, it shows how good our trade-off front in general is. We have an alternative metric which is called coverage, and this measures. So we divide our quadrant in sectors and calculate the percentage of sectors in which we have some solutions. So this is a useful metric to measure diversity of the found solutions. And in practice, it means higher coverage means that the practitioner has more options to choose from different trade-offs. And we use both of these metrics in our evaluation of different algorithms. So one of the main results we have is shown here for precision recall optimization on the Higgs tabular data set. As the metric, we use logarithmic difference between approximate ideal hypervolume and achieved hypervolume by different timestamps. So lower is better. And we see that MO-PBT nicely outperforms other baselines. So we have a simple random search, we have MO-ASHA, we have Bayesian optimization version of MO-ASHA. We have PBT applied to optimizing single objectives, so precision and recall. And we also have PBT with different scalarization techniques. And the MO-PBT outperforms all these baselines. So a different example on a different data set. So here we have Cypher10 and accuracy versus adversarial robustness optimization task. And here at the end of our search, MO-PBT is also the best performing algorithm. However, we might notice that in the beginning, so actually up to 1000 minutes of search, MO-PBT is lagging behind MO and BO MO-ASHA. And the explanation for that is that in our setup, we have number of parallel workers smaller than the population size. So in MO-PBT, networks, not all networks. So in MO-PBT, networks are not fully trained by, let's say, minute 500, though in MO-ASHA and BO MO-ASHA, some networks are fully trained. And that explains why MO and BO MO-ASHA has better performance at, let's say, minute 500. But if we could have more parallel workers, so equal or more than population size, then this problem would disappear. As in this example, the plots should look like kind of like this. We also compare MO-PBT to QNEH, the Bayesian optimization algorithm. We note that it's not fully parallel because batches of solutions are sampled sequentially. However, it's still a powerful MO optimization algorithm, so we compare to it too. And we see similar pictures to the previous ones. So in some cases, MO-PBT has better anytime performance, and in some cases it has significantly better performance at the end of training, but in the beginning and in the middle it's lagging behind because no networks are fully trained in the middle of our search, and yeah, this is why it can catch up only later. We pay quite a lot of attention to scalability of MO-PBT, and first of all, we study whether it scales with a larger population size and for more than 2 objectives. So in our experiment with more than 2 objectives, we take accuracy versus 2 different fairness metrics. And this is done on adults tabular dataset. It's quite commonly used benchmark for fairness. And we have different population sizes here. And we see that MO-PBT, first of all, it scales nicely with larger population size. So if we use more computational resources, we have better performance as we'd like to have. And also we note that it doesn't have any visible problems with handling more than 2 objectives. So 3 in this case is also fine. Then we study whether it scales to search spaces with a larger number of variables. And on the search task of accuracy versus robustness on Cypher 10, we have 2 search spaces. One is small, so has only 5 search variables, and one search space has 31. And we see that MO-PBT also doesn't have any problems with operating in larger search spaces. So performance has slightly improved, and it's a nice property to have also because maybe in some search task we'd like to have more variables to search from. So we also carefully study how exactly the obtained non-dominated fronts of solutions look like. So the first example is on the precision recall task on Higgs dataset. So we plot all obtained non-dominated solutions, and we see that in both hypervolume and coverage metrics, MO-PBT outperforms MO-ASHA, and we can see that the front has fewer gaps and has slightly better quality. A different example, so Cypher 100 dataset, here we see similar picture. So MO-PBT front has much more solutions. So for practitioner, it means much more options of different trade-offs between accuracy and robustness to choose from. And quite similar picture on accuracy versus fairness on the Celiba dataset. So better performance in both quality of solutions and diversity of them. We also compare MO-PBT to PBT with the single objectives and scalarization in order to understand better on which areas of the search of the objective space MO-PBT is focused while searching. And we see here that, as expected, single objectives and scalarization techniques are more concentrated in terms of the focused objectives. And MO-PBT solutions in MO-PBT are scattered quite nicely along the whole trade-off front. And this is explained by the fact that we use a naturally multi-objective technique, which doesn't explicitly focus on just some areas of the trade-off front. Instead of it tries to optimize the whole trade-off front as one. And yeah, some discussion here. So in all these experiments, we performed search in the discrete search space. So it has some pluses and some minuses. One benefit of this is better interpretability. For example, if we can explicitly switch off fairness regularization, so we can obtain solutions without it. And because it's discrete, and one of the options is just not having any regularization in terms of fairness. But it has some downsides as well. So we have a less fine-grained search because we have to search from a number of predefined options. But I'd like to note that we can also have real valued search spaces if we define exploration operator. And in fact, in the original PBT paper, some exploration operators for real valued search spaces were used. So we can, in theory, take them and apply them to MO-PBT in order to search in real valued search spaces. So one of important parameters to set by user of MO-PBT is population size. And it's not super nice in the fully AutoML paradigm of because the user has to choose population size manually. So automatic population sizing would be nice as a future work direction in order to have a fully AutoML paradigm where a user doesn't have to set any hyperparameters at all. And also, the current version of MO-PBT is not applicable to neural architecture search directly because it assumes that all architectures are identical in the population. Theoretically, it would be nice to also have to also apply it to NAS, and it's another possible future work direction. So to conclude, we introduced a parallel scalable algorithm for hyperparameter optimization, which we call MO-PBT. And in experiments, it was shown to be a state-of-the-art algorithm. Compared to different modifications of single objective PBT, we show that naturally MO technique, domination-based ranking, works better for multi-objective problems, and MO-PBT outperforms all considered versions of applied single objective PBT to multi-objective problems. And also it outperforms other existing algorithms such as random search, which is simple baseline, also MO and MO-ASHA, and the Bayesian optimization algorithm QNEHVE. So the paper is available at this QR code if you are interested. And yeah, thank you for your attention. I'd like to thank you again for having me here today, and I'll be happy to answer any questions.